Hello everyone. So in this video we will review the concept of dynamic optimization. As we see, time can be either continuous or discrete, and we have different tools of optimization when we have time as a discrete form and when we have time in the continuous form. We have Lagrangian when we consider time under discrete variable, and we will use Hamiltonian when we will consider time as a continuous variable. After the dynamic optimization, what we will end up is a set of either differential equation, which would be the case when we will consider the dynamic optimization under continuous time, or a difference equation when we will consider the dynamic optimization under discrete time case. So in both cases, we will end up with these equations. Those would be our first order equations, and then we will use some tools to solve those first order equations. So as you can see, there are some parallels that you can draw with the static optimization. The only difference is the static optimization considers only one point in time, while the dynamic optimization considers more than one point in time. In fact, it incorporates the whole lifetime of an economic agent into the dynamic optimization consideration. So let's start with the continuous time case first, and the tool we will use is called the Hamiltonian. And before we start, there are some definitions that we will go through. So there would be a lot of theoretical details that we will not be discussing over here, and we would be focusing on the application of Hamiltonian for dynamic optimization. For more details, you can consult Optimal Control Theory chapter on Alpha C. Chiang book, or you can consult the Annexure A3 from the Barrow and Salai Martin book on economic growth. Both are mentioned in the course outline as well. So our focus would be on the application of Hamiltonian for the dynamic optimization case. So let's review some of the terminologies before we set up the optimization problem. The first is a control variable. The control variable is it would be a choice variable that the economic agent will choose in the current period to maximize the objective function subject to some constraint. The next one is a state variable. The state variable is a variable which the decision makers or the economic agent takes as a given in the current period. But its next period value will depend on the choice that agent makes in the current period. And then we have a state equation. It is defined as the intertemporal changes in the state variable. So it is also known as equation of motion or the transition equation, because the constraints are represented by the state variable, which are dynamic in this case. So that's why we call it equation of motion or a transition equation. So we will always have control variable, state variable, and a state equation when we will be considering the dynamic optimization with Hamiltonian. The optimization problems in words, it would be like a set of mathematical expressions, including the objective function and all the constraints. The constraint include the state equation, or it could be equation if we want to consider more than one constraint, and any other condition satisfied at the beginning or at the end of the time horizon. At minimum, the dynamic optimization, it should include the objective function. It should also have a state equation, and it should have initial condition for the state variable. So these are the three minimum conditions that we should have when we are doing the dynamic optimization case. And we will consider the case of a consumer utility maximization, and for that we will employ the Hamiltonian. And again, our focus will be on the application side rather than theoretical side. So let's start with the consumer utility maximization case of dynamic optimization. Again, let's just see what would be the control variable. Control variable in this case for consumer would be consumption. Consumer will choose current period consumption, and through this they will determine what will be saved or investment. The state variable in this case would be the assets owned by the households or the capital stock, if we assume they are owned by the households. So the transition equation or equation of motion will provide us the changes in this state variable. So the state equation would be the evolution of assets by the households. It will capture the evolution of household by the assets by the household. Let's just see in detail what does it look like. So in words, it sort of says that the asset tomorrow, the assets owned by the households in next period would be whatever assets they have today plus whatever savings they made in current period. So it would be like AT plus 1 is equals to AT plus YT minus CT. If we want to represent it through a mathematical expression, it would look like this, where we are saying that the changes in asset, which is nothing but saying over here, asset tomorrow minus asset today, would be equals to whatever household income that they have minus their current consumption. So if we want to see WL would be the total labor income, and R times A would be total income earned on previously held assets minus their current consumption. So this is the equation of evolution of asset owned by the households. So this would be the state equation in our case. What we want to do is that we want to convert this equation into a per capita form, and for that we would say that in per capita terms, C over L would be the small c. So small c here would represent per capita consumption. Similarly, per capita asset would be capital A divided by capital over L. And we're also assuming that the population grows with the rate of n, which is another way of saying L dot over L is equals to n, or dl over dt is equals to n. Expression, and then we will try to write this equation in terms of small a and small a dot. The reason we are doing is that it's more conventional. All the textbooks analysis are provided in per capita terms, and it also provides more insight as compared with if we analyze in not per capita term. So this is the reason we're doing it. It would be more helpful for the analysis. So what we're doing is that we just divided this equation by L on both sides. So we got 1 over L over here. W over L will give us only W, and this small c is C over L. So we divided this equation by L. In the next step, what we want to do is that we want to find out a value for this to replace over here. To do that, what we are doing is 2 or 3 steps of algebra. We would differentiate A over L with respect to time. And then whatever result we will get, we will substitute that over here. So if I differentiate A over L with respect to time, as both A and L assets are themselves function of time, we'll apply the product rule over here, and this will give us this step. I'm just writing capital A over L as small a. This as it is comes over here, and over here I have differentiated 1 over L with respect to t. So that would be minus 1 L raised to the power minus 2, and then dl over dt. and L raised to the power minus 2, I can just write it down L times L in the denominator. So with a little bit of a simplification, I can see that I have a value over here of 1 over L dA over dt, which I can bring on this side. Right, so let's just simplify one more step, and over here I can write d over dt of small a as a dot, and this is the expression that we're going to need, minus a over L as small a, and then dl over dt over L is n, as we said over here. And what we need is the value of 1 over L dA over dt, and we're going to substitute this into this state equation over here. So when we substitute, what we get is this. This equation is all in per capita terms, and this is what we will use in our Hamiltonian dynamic utility maximization for consumers. So this will be our budget constraint, and as we can see, it is dynamic because it involves the rate of change over here, and the value, what it says is that the value of tomorrow's assets will depend on today's action. So this is the budget constraint that we will use for the optimization. Okay, so we looked at the constraint, and for the utility maximization, we know there has to be an objective function. So just look at the objective function. The objective function for the consumer would be like this shape, where we are saying is that the household utility at time t is equals to 0 is the weighted sum of all future flows of utility. And this e raised to the power rho t is used for discounting, which is another way of incorporating that utils are like valued less the later they are received. Another way of incorporating the fact that dollar today is not the same as dollar, let's say, 10 years later. So we will discount the future consumption. So this is a discount factor, discounting that we are using. And we also want to convert this utility function into per capita form. Over here, what we have is as consumption as it is. We want to divide it by the L. For that, we have to do a little bit of a manipulation. We already assume that the population grows at a rate n, and this is just another way of saying the same thing. How? Let's just, if we just take a log of this expression and then differentiate it with respect to t, we will get L dot over L equals to n form. So we have small t as capital C divided by L, which is per capita consumption, and for L, if we substitute this value, e raised power nt, it means that consumption as it is would be equals to per capita consumption times L. So if we substitute for capital C small t times L, where L is equal to e raised power nt, we will end up with this expression. So we will have this utility function, objective utility function, lifetime utility function for a consumer, and we will use this to set up the Hamiltonian function now. So let's set up the Hamiltonian function over here. The Hamiltonian function would look like this form, where we will have a utility function over here, which we just established, plus v of t, and then we will have an equation of motion for the assets at the budget constraint. So this is how we set up the Hamiltonian. So Vt over here is the present value shadow price of income, and it is somewhat like the case of static optimization, but in this case it is dynamic. Okay, so now we move on to driving the first order conditions. We will employ the conditions over here, there would be partial j over partial c with respect to control variable. We'll set it equals to 0. This would be our first FOC. The second FOC would look like this, where we will have v dot equals minus partial j over partial a. A is our state variable. So for this second FOC, we will compute this value and substitute in this expression. For the first FOC, we will find partial j over partial c. So let's just find the first FOC. So if we differentiate this with respect to c, I will get u prime c as it is, and then I have over here c, there would be a minus 1, so I'll get vt as it is equals to 0. I can simplify this a little bit more and I will get this expression. So this is this is like a simplified version of our first FOC, and then we move on to the second FOC over here. For that, we will find partial j over partial a, and then we will substitute this value over here. If we differentiate with respect to a, since a appears in this term, and over here I will get r minus a, and then this v of t will come as it is over here. And then I substituted that in this expression, I get this simplified version. So what we have to do now is to simultaneously solve these two expressions and remove vt. That would be our second step. Okay, so we have these two FOCs, and our goal is to solve them simultaneously and remove Vt or V dot t. One way we could do is that since we already have the value of Vt over here, which does not involve any Vt expression on the left hand side, we can just directly substitute Vt over here in this side. But we still need a value of V dot t. The way we can get it that we differentiate this FOC with respect to time, that will give us V dot t, and then we substitute that value over here. So let's just use that method. You can use any other method. There could be different ways of solving this. So let's just apply this method and solve them simultaneously. So we're going to differentiate with respect to time first FOC. Notice that over here we have two functions which involve time. U prime c is also a function of time, and this exponent function also have t, so we'll have to use a product rule over here. But for when we will differentiate this function, we'll have to use a chain rule because u prime c is a function of t. So we'll apply both product rule and then we'll use the chain rule as well. So let's just do it. So let's just say this is our first function. We're differentiating the second function with respect to time. So this will be u double prime c. Then we'll take the derivative of c. This will come over here. So first function, differential of second plus second, and then we differentiate this with respect to time. This is straightforward. And this will e raised power n minus rho t, and then we'll have n minus rho as a multiplicative term on this side. On the right hand side, this would be v dot t simply. Next, what we do is that we divide it by v of t on both sides, and then we substitute its value as well. And we divide it by v on both sides, and when we substitute its value, this exponent term will get cancelled out when we will divide it by value of vt, which is u prime c of t, and e raised power n minus rho t. So this exponent term will cancel out, and then we will have the value of v dot over v as well. We can substitute this value from second FOC. V dot over v is equals to minus r minus n. So we substitute that value over here as well. And for simplicity, we can just remove the t argument over here. We know they're all function of time, so for simplicity, we are sort of removing them, and then if we solve it one step further, we will get this expression. This equation is known as the Euler equation, and what it says is that the household choose consumption so as to equate the rate of return or to the time preference. So this is an important expression in macro for both continuous time case and discrete time case that you will see. It describes the evolution of consumption along an optimal path. So this is where we have to reach over here. As you can notice, our FOCs were the differential equations, and we solved them, and then we ended up again at a differential equation in this case. This would be a second order nonlinear differential equation. It involves a second order differential over here. So we will later on in the core courses, you will see the methods to solve those equations. And over here, we're going to use one more step of the application. That is, let's just take a specific form of a utility function over here. And so far, we have been using utility in the general form. Let's just use a specific functional form, which is of this shape. And what we need to do is that by using this utility function, we want to compute the value for this expression using this utility function. So we would need the value for u prime c from here and u double prime c. So if we differentiate it with respect to c, we will get this value, which would be c raised power minus theta. And if we differentiate with respect, again, this expression, we will get this value. We take these two values and we substitute in this expression, and what we get is c dot over c is equals to 1 over theta r minus rho. Again, there's a lot of economic interpretation that goes behind this and that you will see in the core courses. Right now, our focus was sort of again on the application of Hamiltonian by using this utility function.